So in chapter 9, we're going to take a look at inference for quantitative data and specifically means. So we're going to start about talking about confidence intervals for means. A farmer wants to estimate the mean weight in grams of all tomatoes grown on his farm. To do so, he selected a random sample of 4 tomatoes and calculated the mean weight in grams to be 110. Assuming the population of all the tomatoes in his field are normally distributed, use the sample mean to create a 99% confidence interval for the population mean. Suppose the standard deviation from his tomato field in the past has been 40 grams. So in this example, we know our standard deviation, which changes how we run our confidence interval versus not knowing our population standard deviation. So in this case, the standard deviation we're given is a population standard deviation. Okay, so our population standard deviation is 40. So the first part of our confidence interval is to figure out what our parameter of interest is and decide our confidence level, or our Z critical value. So we don't typically write the parameter of interest, but we do like to make sure we know what we're doing. So what we're trying to find is the true mean weight of all tomatoes. Okay. And then we also want to find our Z critical value. Now we're going with a 99% confidence interval, so an INV norm. Our area would be 0.005. Mean of 1, 0, standard deviation of 1, and it gives us 2.576. Okay. Second step, we want to check our conditions. Okay, so random, we want to make sure it states a random sample, which it does. Independent, our sample size 4 needs to be less than or equal to 10% of, in this case, all tomatoes, which there's at least 40 tomatoes, so we're good there. And last, we want to check normal. So remember, normal is different for means than it is for proportion. So for means, there's one of two things. Either you are given that the distribution is already normal, or your sample size has to be greater than or equal to 30. And here it tells us that it's normally distributed. So we're good there. So we have met all 3 conditions. So now we want to construct our confidence interval. So remembering back from chapter 8, we have our point estimate plus or minus our critical value times our standard deviation. Okay, that's the generalized formula for a confidence interval. If we use what we're given, so our point estimate in this point is our x bar, plus or minus our Z critical value times, and then standard deviation is standard deviation over the square root of n. Okay. So going back in the problem, the current weight, average weight is 110 for our sample, plus or minus our 2.576 times our standard deviation of 40 over our square root of n, which in this case is 40. So if I do 2.576 times 40 over the square root of 4, we get 110 plus or minus 51.52. So first value is 110 minus 51.52, which gives us 58.48. And our second value is 110 plus 51.52, which is 161.52. We are going to find that with means, our confidence intervals are going to be a lot larger than the proportions. Okay. And then lastly, we want to write our sentence. So it starts the same way as proportions. We are 99% confident. Now here's where it changes. All right, so there's a couple ways you can write this, but it's most important that no matter which way you write it, you remember the units. So with means, we're now going to have units. With proportions, we were dealing with percentages, so we could leave it as a decimal. But for means, we got to make sure that we remember the units. So in this case, we're talking about the true mean weight of tomato plants will be between, and then 58.48 kilograms and 161.52, sorry, not kilograms, grams. Grams and 161.52 grams. Okay, so we reorder it a little bit. Instead of putting the proportion first and then our situation and context, we put our context first and then the two values with units. So what we just created is called a one sample Z interval for means. Okay, so when we were doing confidence intervals previously, we made an assumption that we knew the true population standard deviation, which, doesn't really work because we're trying to find a confidence interval that could contain the true parameter. So when we don't know the population standard deviation, we have to estimate it from our sample using sample standard deviation, which we denote with the lowercase s. However, when we do this, the test statistic z changes, and it's now called a t-statistic, and that has a new density curve associated with it. So t-statistic, something we're going to introduce for means, different than our z statistic. So our new distribution is not exactly like our standard normal curve, but it's very, very close. So the center is still at 0. It's still bell-shaped. Its spread is slightly greater than the standard normal distribution. So with the spread for our standard normal distribution, it was 1. Okay, but now the spread is slightly greater than that. And it has more area in the tails because of this. So unlike our z interval, which for proportions, which was not, our z statistic was not based on sample size, in t-statistics, it is dependent on the sample size, which is used to find our sample standard deviation. All right, so the dependence that we have on the sample size is taken care of via something called degrees of freedom. And degrees of freedom are always your sample size minus 1. Okay. And then we just have a review of everything that was just stated. So t-distribution, similar in shape to the standard normal curve, symmetric about 0, single peaked, so they have that single like max and is bell-shaped. The spread is a little bit bigger because we substitute an estimate for our sample standard deviation, and it introduces more variation. And as your degrees of freedom increase, the more it approaches a standard normal density curve more closely. So I'm going to draw some graphs so we kind of get an idea of what this looks like. So here, the black is going to be our standard normal curve. So let's draw our mean. Let's see if I can get it. There we go. That's a much better curve. I'm going to move my mean slightly. So my mean is at 0. Along the bottom here is where our test statistic is gonna fall. The black one is the standard normal. Okay, this is what we use Z. Okay, now if I had a t-distribution where my degrees of freedom were 5, it's not gonna look as bell-shaped. It's gonna look kind of like this. Sorry, I'm very bad at drawing the graphs. Okay, so this is t-distribution with degrees of freedom equaling 5. Now, if I increase my degrees of freedom to 20, it gets even closer to the standard normal. Okay. So there is a point in degrees of freedom where it reaches a value so large that it's pretty much normal. And that's for any degree of freedom pretty much bigger than 100. The value is so large that it pretty much just assumes our standard normal distribution. So finding area probabilities underneath this curve, I could give you a table like we had for our z-test statistic, but we're actually going to use a function in our calculator. It's called the TCDF function. So here's just a snippet of what the table looks like. So you have your degrees of freedom in your column, and then your row is your probability for your tail. So it's whatever your, so you take, if like I'm doing a 99%, then my tail would be 0.005. So it's similar to when we were doing it for proportions. So when you're calculating our t critical value, our t statistic, I'm going to do it using the calculator function, which you get to, you do second vars, and then you want number 4, which is INVT. So the 4, so we're going to look at 4 examples here. We're going to look at 2 different percentages, and then we're going to look at how, even if you're looking at the same confidence, changing your sample size severely affects your t critical value. So we're going to start with a 90% confidence interval for n equals 30. So if I'm just looking at 90%. Having a terrible time drawing my curves. Okay, so we're looking at in the middle being 90%. So that means each tail, we're looking at 5%. And we have our two t critical values. You have a positive and a negative at the 5%. Okay, so if we're going to use our calculator, we're going to go to the INVT, okay, and our area is going to be 0.05, and our degrees of freedom are going to be 29, because again, degrees of freedom, one less than our sample size. So 0.05 comma 29. And that is going to give us a t critical value of 1.699. And again, we ignore the negative here just like we did with the z critical values because of that plus or minus in the formula. Okay. I'm not going to keep drawing the curves. So for 95%, our area is going to be 0.025 with degrees of freedom of 19. And that gives us a t critical value of 2.093. Okay. It doesn't do any good to memorize any of them, kind of how with proportions we might have started to memorize them, because for the t critical values for means, they change based on your sample size. Okay. Now we're going to look at a 96% confidence interval for our sample size of 230 and our sample size of 5. So in both cases, our area is going to be 0.02, but our degrees of freedom are what changes. So for our first one, our degrees of freedom are going to be 229. And we're going to get a t critical value of 2.066. Okay. If our sample size was decreased to 5, still an area of 0.02, but this time our degrees of freedom are 4. And we can see that our t critical value increases to 2.999. So we can see how the larger the sample size, the smaller the t critical value. And we want to have larger sample sizes anyway, just based on experience. So it always works best. That way we can make sure it's more normal anyway. So when we're constructing a confidence interval for a population mean with an unknown standard deviation, so we don't know the population standard deviation, okay? So our 3 conditions. So we still have to meet random. So random assignment comes from an experiment usually. Or we can have random selection, which is when it mentions an SRS, okay? Normal, I talked about this briefly in our first example. So if the sample size is less than 30, you have to make sure the original sample is normally distributed, all right? Typically, it's going to mention the words normally distributed. Secondly, if the sample size is greater than 30, then we don't need to know anything about the original population being normally distributed, because our central limit theorem says it's going to be normally distributed anyway. It could say it, but also have a large enough sample size. If it says both, all the better, but it's not likely to. And then lastly, we have to have that independent. So individual observations have to be independent. So our sample size has to be less than 10% of our population size. So n has to be less than or equal to 0.1 times capital N. Okay. So once the conditions are met, then we can construct our confidence interval using our t statistic in the same way that we would use our z statistic. So just to kind of compare the two formulas. So for a t interval, it's x bar plus or minus our t test statistic times our sample standard deviation over the square root of n. Okay. For a z interval, It's x bar plus or minus z critical value times the population standard deviation over the square root of n. So it's pretty much the same formula. All right, one's used if you have sample standard deviation, the other's used if you have population standard deviation. That's the only difference in the two. We will mostly be using the t interval instead of the z interval. Please let me know if you have any questions about doing a confidence interval for a mean, especially when it comes to finding your t statistic.